Thank you very much, Chairman, and thank you everybody for being here. I would like to thank people who organized this event, Professor Yang, Professor Tamura, Professor Yan, Professor Lee for inviting me. Thank you everybody, and I hope my talk contributes to many great talks that we heard over the last 1.5 days. From that point of view, I will be talking today about deterministic and constrained stochastic models of thunderstorm winds. Before, I would like to also introduce in one slide my research group and what we are doing. So my first research area is really thunderstorm winds, and I'm dealing with downbursts and tornadoes. And this is my core research. I use all kinds of methods from anemometer, surface radars, surface lidars, wind tunnel techniques, and so on. Today, I will talk about an analytical model that I developed over the last several months that concerns downbursts as well as tornadoes, but I will only talk about downbursts today. I also do research in the field of urban boundary layers. In my group, we investigate mean flow and turbulence using mostly lidars and numerical models. And also I do research in resilience and sustainability, such as wind engineering, natural hazard modeling, greenhouse gas and pollution modeling. I have a student doing indoor air quality and also started working in the field of system dynamics. Okay, so going back to this presentation, downbursts. What are downbursts? Well, here is a thunderstorm, a base of a thunderstorm cloud, and you can see here precipitation zone. This is in Tucson, Arizona. There is already downdraft in precipitation zone, but right now there is very localized downdraft known as downburst or microburst that spreads radially, impinges on the surface, spreads radially, and can create very high intensity winds. Winds in downburst can exceed 70 meters per second close to the surface. Maximums occur very close to the surface, between 50 and 150 meters, so they are completely different to atmospheric boundary layer winds. Now, in terms of why do we care about these events? Well, economic losses that convective events like downbursts cause are huge. This is in Canada. Blue is Quebec, red is Ontario. We see tornadoes, tropical cyclones, and winter storms create this much cost, but convective storms that include downbursts over a year cause much more damage. In fact, tornadoes are the most damaging per event, but downbursts are more frequent, so we get much more damage. Here is the occurrence of downbursts across the southern border of Canada. These are those red and blue spots, and there are many of them, much more than tornadoes. If you look into, I couldn't find data for downbursts over China, so that would be an interesting research to conduct. But if we just look thunderstorm days in China, you can see, here is the legend. You can see that certain regions exceed 80 thunderstorm days per year, which is very, very significant. Not all of them cause damage, but some of them for sure. And the trend seems to be variable, associated with climate dynamics over the last several decades. So as we know, thunderstorms create damage. And here is a picture that I took of damage caused to trees. Here is a photograph of a damage to a barn in Ontario. Here is a photograph of damage caused by thunderstorm winds in China. And this is a photograph of damage caused to my cottage in Serbia that my mother photographed. And if this presentation was longer, I would present a case study about my cottage, but I will skip it in this. Now, first technical point is, how do we characterize damaging winds? In 70s and 80s, Fujita proposed the quarter-mile wind, and that's the maximum wind speed of any quarter-mile passage of wind at the damage location. So that's an old school of characterizing wind damage, where time averaging is not fixed, but distance is fixed, and one can go between time and space. But today we use 3 or 5 second gusts, depending on the code. So in my model, this is now very important. The model that I developed can work on either of these two approaches, whether you report damaging gust as a quarter-mile wind or a 3 or 5 second gust. Now, just one slide about general characteristics of downburst winds. Here, black is atmospheric boundary layer winds. Gray is downburst winds. They have this nose-shaped profile, maximum very close to the surface. As you can see, they are non-Gaussian, and you can also see, they are non-stationary and non-Gaussian. Kurtosis is almost 6, but you didn't have to calculate it to figure out over there they're non-Gaussian. So what is motivation for my research that I conducted over the last several months? Well, thunderstorm winds can cause damage to the built and natural environment. We all know that. And this damage these days is very well documented. Everybody has a phone, and everybody can take a picture of damage. And even government services are doing it systematically these days. So the question that I really wanted to answer is the following. Using readily available information about the storm that caused damage, can we reconstruct time history of wind velocity at the location of the reported damage? Or in much simpler words, if there was an anemometer over there, what would it measure? That's the question that I'm trying to answer. So let's just first see what anemometers generally measure when there is a thunderstorm. So here is a thunderstorm wind event in the Netherlands. Measurements at 3 meters above ground. Forget about these arrows for now. That's from previous research. X-axis is time. You can see that we have stationary wind, then downburst happen, and again we have stationary ABL wind. This is at 3 meters, this is at 60 meters, this is at 100, this is 180 meters on a 230 meter tall tower. Black is wind speed, gray is wind direction, secondary y-axis. And we see similar signatures around the world. It's a busy slide, we don't have to go through it, but thunderstorms are non-stationary. So they are well documented in many cases. Now I would like to talk about thunderstorm wind decomposition technique. That is the backbone of my model that I propose. Here is a thunderstorm wind record. And if we use the classical Reynolds decomposition, where we have a mean that is stationary and then fluctuations around the mean, that doesn't work because this is non-stationary process. So what we do, we replace this equation with the moving mean, usually 30-second or something else. And then here we have steady state atmospheric boundary layer wind, thunderstorm, steady state atmospheric boundary layer wind. And then we have residual fluctuations that are unfortunately also non-stationary, but we can rewrite them as a product of slowly varying standard deviation and something called reduced turbulence fluctuations. And here I present these. This is slowly varying standard deviation. And here are residual fluctuations that are now completely Gaussian and a stationary process. And then substituting that into the equation above, we get this equation. And fortunately, nature was kind, so that the turbulence intensity is pretty stationary during thunderstorm event. And that has been demonstrated many, many times. So one could say that generalization of Reynolds decomposition to non-stationary winds looks something like this. And that's the equation I start from. This is just demonstration that these turbulent fluctuations, reduced turbulent fluctuations, are indeed Gaussian, zero mean, unit standard deviation, skewness 0, kurtosis almost 3, and they are also following turbulence spectrum in the inertial subrange. And here are more cases of decomposed velocity records, even decomposed velocity records from wind tunnel measurements that we did. So another conclusion, very simple, is that thunderstorm velocity decomposition technique is well developed and tested. So can we use it together with damage information to reconstruct thunderstorm velocity record that caused this damage? By the way, I also wanted to blatantly advertise my YouTube channel. You can follow more about atmospheric sciences, wind energy, wind engineering, and so on. Previous speakers very seemingly incorporated their books into talk, but I didn't know how to do it, so I just throw a slide. At any rate, going back to my talk, so if we start from this equation, over here is just what these terms are. The first, we need to propose a model for mean wind speed. And I used model proposed by Professor Karagolia and Lee in 2018. So it's a simple half cosinusoidal fluctuation. And the model basically looks like this. So we have atmospheric boundary layer winds, thunderstorm of some duration, atmospheric boundary layer winds. Now, what are knowns in this model, in my theory? Knowns are storm duration. That is very simple to determine. Knowns are pre-storm atmospheric boundary layer winds. They can be measured from nearby weather station. But unknown, which is the core of my research, is this VM, this maximum of slowly varying wind speed. That's the unknown. Okay, that's mean wind speed. How about these fluctuations? I followed the grades of Davenport and Fujita. They said in the absence of anything better, represent fluctuations as a sinusoidal fluctuation, and that's it. So I did that. Now here, I am claiming that period of turbulent fluctuations is known, but tricky. I'll mention it later. And turbulence intensity is very known. That's simple to estimate based on the height where the damage occurred. So if we combine now, this is my starting equation. I use Professor Karagolia's model for mean wind, Davenport Fujita model for turbulence. I get this as my wind speed equation. And that would look something like this. So sinusoidal fluctuation superimposed on a sinusoidal fluctuation. So unknowns, to recap, are peak gust and maximum of the slowly varying wind speed. So how do I get it? I get it because damage is known. And damage, as I said, is either known as the fastest quarter mile wind or 3 or 5 second gust, depending what is the standard that people use to report damage. And here is just, of course, simple kinematic equation. What is the quarter mile wind? Well, from this graph, I can determine fastest quarter mile wind by integrating velocity over time. And that's what I did. So over here, d is quarter mile. I take integral between here and here, and I integrate my velocity. And basically, I will get this. So quarter mile or some other mile, whatever, is integral of that. So I can solve this integral. Everything is known except Vm. I can solve the integral, express solution in terms of Vm, and I have my maximum slowly varying wind. And here is the solution of these various integrals. They are not complicated, but just many of them. So this is the final solution that is here. So maximum of the slowly varying wind is this huge equation that came from damage assessment. This is, if you want, you can simplify it a little bit like that if you neglect few terms. And then we can also find instantaneous peak, knowing that it happened at time t equals 0. So basically, that's the recap of this graphically. How about this period of turbulent fluctuations, P? That's a tricky business because you have to pick only one number. So you could take barocenter of turbulent spectrum, what Professor Solari taught me. You could also calculate the number of up crossings. In this case, for a time series, number of up crossings was 1.5 second, average number of 0 up crossings. And that's very similar to Roncallo and Solari, who did similar analysis and got 1.8 seconds. So how do we use my model? Example, a reporter quarter mile or anything, thunderstorm wind that caused damage somewhere here is 35 meters per second. Reconstruct the velocity time series at the location of the reported damage. It's like a high school problem. So we go to first step, find atmospheric boundary layer winds. Go to nearest weather station. Let's say there were 5 meters per second. Step 2, ask people how long was this thunderstorm? 10 minutes, 15 minutes, 13 minutes, you take average. Model is very robust on this. Estimate turbulence intensity based on the height and assume some value for the period of turbulent fluctuations, and you get this as reconstructed. What is really valuable about my model is not this time series, but you give me one number, 35 meters per second, I give you two numbers. And these two numbers are fundamental property of thunderstorm, not property of the damage that people assessed.